Hi everyone, my name is Alima and today we'll talk about circuits and capacitors. We go over the introduction, the experiment, the observation and calculation, the results, and the conclusion. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, to examine the behavior of ohmic resistors and capacitors, and measure the actual values of conventional current and potential differences in the circuits. To help us with the experiment, we use Ohm's law that states that the voltage across the circuit is equal to the current times the resistor, the capacitance which is equal to the charge over the potential differences, and Kirchhoff's law rule, who stated that the sum of currents or voltages at a node equals zero. For this experiment, the time dependence value for a resistor capacitor circuit was 5.995 seconds. The first step was to construct a circuit using the circuit construction kit from Colorado PHET project. We used two 1.5 volt batteries, a 47 ohms resistor, a 100 ohms resistor, and two ammeters. Using Ohm's law and the loop rule, we sum the voltage differences in the circuit, and we had two resistors in series, which gave us the total equivalent resistor. And for the conventional current across the circuit, we have by calculation 0.02004 amps. The tested current, as we saw in the previous slide, showed 0.02, which is pretty close to the calculated one. When we reverse the ammeters, we obtain the same results for the current and the resistors in series. After replacing an ammeter with a voltmeter, the reading were for the voltmeter 3 volts and for the ammeter 0 amps. Those values are explained to the fact that current does not flow through the voltmeter due to the resistance, which is why the ammeter reads 0 amps. So we decided to measure difference potential at between two different spots in the circuit that we label A, B, C, D, and so on. And those are the delta V on the second part of the table, and the sum of the voltage stated by Kirchhoff's rule should be equal to 0, and in our case we got 0.04, which is pretty close to 0. Here is the graph of circuit voltage, where we can see this electric field that is the negative gradient of the electrical potential, and the electric field is larger at resistors and batteries. For our RC circuit, we used a resistor and a capacitor, so a 10 ohms and a 20 ohms resistor, 9 volt battery, and 200 millifarad capacitors. When the capacitor is charging, the light bright and slowly fades off. It took 6.25 seconds to charge with the 10 ohm resistor and 8.5 seconds with the 20 ohm resistor. When the capacitor is discharging, the light is bright first, then slowly fades. For the results, we computed the voltage versus time, and with the formula we deducted 1 over RC, negative 1 over RC, which is the slope of the graph, and we deduce RC, the time dependence, equal to 5.995 seconds. The experimental and calculated value of the time dependence were very close, 5.995 seconds and 6.25 seconds, which implies the reliability of the experiment. So what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? Real-life emitters have internal resistance, which means that the value obtained will be less than what obtained in this virtual experiment. What if you were doing this lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? In the case of an ideal model, the capacitor will charge instantly. However, in real life, because there will existing resistance throughout the circuit, the capacitor will take longer to charge. This is the end of the presentation. Thank you.